Hello, this video will explain the concept of coronal mass ejections and how to predict their trajectories. This is a quick overlook of the video. Coronal mass ejections are violent bursts of charged particles from the sun. When they reach Earth, they can potentially damage satellites and immobilize power grids. Coronal mass ejections are dangerous, and it is important to know how much time it takes for a CME to reach Earth so we can have a lead time to safeguard our infrastructure from any harm. The purpose of this experiment was to find a relationship between a CME's mass and the time it takes for it to reach Earth. The hypothesis was, if a coronal mass ejection has a small mass, then it will take less time for it to reach Earth than a coronal mass ejection that has a greater mass. SOHO, which stands for Solar and Heliospheric Observatory, is a satellite that orbits around the Sun in sync with Earth. Their website provides information about the data required to explore the hypothesis. The video recordings from the SOHO satellite were analyzed, and the data such as the distance of a particular CME from the Sun at different times was documented. A Java program was created which calculated the velocity, acceleration, and the time it took for a CME to reach and cross the Earth. The mined data was fed into the program, and it calculated the results. After analyzing all the data, I had found that the CMEs with the greater mass took the least amount of time to reach Earth, and the CMEs that have the least amount of mass took longer periods of time to reach Earth. This contradicted my hypothesis. My project can predict the lead time we have to avert the damages to our electronic and electrical infrastructure in case there is a direct collision. My hypothesis of the trajectory of a CME is, if a coronal mass ejection has a small mass, then it will take less time for it to reach Earth than a coronal mass ejection that has a greater mass. Basically, if a CME has less mass than another CME, then it will take less time for it to reach Earth. Think about this for a moment and create your own hypothesis for the trajectory of a coronal mass ejection. I have done this experiment to predict the trajectory, and I have done so by creating a Java program that would predict the trajectory based on few inputs from the user. The creation of a CME starts from the Sun's core. A specific nuclear reaction called the proton-proton cycle enables two hydrogen atoms to react together to form helium atoms. Through this process, according to the famous equation E equals mc squared, there is a total of 7% loss of mass. This mass is converted into energy. Also, throughout the process, many electrons are released as plasma. Over millions of years, these electrons can travel through the layers of the Sun, eventually reaching the photosphere. Here, the magnetic field of the Sun is always rotating. When there is a concentration of magnetic field at one place, a spiral known as a helix forms. Once this helix snaps, then a rush of plasma rushes out of the photosphere and into the solar system. This is known as a coronal mass ejection. This is my background research. According to the article, Coronal Mass Ejections and Magnetic Storms as found in the World of Earth Science book, CMEs are violent bursts or charged magnetic particles in gas from the outer coronal layer of the Sun. The ejections launch the particles in specific directions, some crossing the Earth's orbit. They travel on solar winds. Solar winds are continuous, but CMEs are defined when there is an increase in particle mass that are able to generate a magnetic storm. CMEs are often associated with the sunspot cycle. During a solar maximum, several CMEs a day are normal. During a solar minimum, one a day is normal. The last solar maximum was expected to be in 2013, but it started early on 2011. Earth's magnetic sphere is so strong that it protects Earth from being hit by CMEs by deflecting it and changing the course of solar wind. This is also known as the Bush shock. This happens because when the Earth's magnetic sphere meets with the solar winds, a shock wave is created. A magnetic sheath is created, which protects the magnetosphere below it, extends out to the ionosphere. CMEs have a major effects on Earth. One good effect of CMEs have on Earth are the aurora borealis and the aurora australis, respectively known as the northern and southern lights. The auroras are created with the interaction of the Earth's magnetic field and the ionic gases, protons, and electrons on the solar winds traveling by. CMEs can also have a bad effect on our life on Earth. Astronauts who are in the ISS during a geomagnetic storm can develop cancer from the radiation. In more serious cases, astronauts can receive serious burns. The circuits in the satellites can also be destroyed by the imbalance of charged particles. The excess of electrons can cause telephone lines, radio stations, and GPS systems to become dysfunctional due to an energy shortage at the power center and power grids. Animals can also be affected. Geomagnetic storms caused by CMEs can affect the magnetic field of the Earth. Birds who rely on internal magnetism abilities will lose their sense of direction. These are the materials and procedure that explains how I created the program. I want to go to data collection, and if you have time, I want you to check out this website in the bright blue on the screen. This will take you to a huge database that NASA has collected. In 1995, NASA has sent out a satellite called SOHO, which stands for Solar and Heliospheric Observatory. This is located at one of the 5 Lagrange points throughout the solar system. At these points, the satellites can observe the entire sun. SOHO has been taking pictures and videos from the LASCO camera of the sun's activities since 1995 up to 2014. I collected all my data from this website. I had to find the distances CME traveled during certain time periods, and then I inserted this info in my program. The program would calculate initial speed, acceleration, and average time it would take to reach Earth. Here are a few data points that I had collected through the experiment. Let's look at this graph. Remember the hypothesis that you had created in the beginning? Check the graph and see if your hypothesis matches up. The graph displays the relationship between the mass of a CME and the time it takes for the CME to reach Earth. My original hypothesis was that if a CME has less mass, it would take a shorter amount of time to reach Earth. Looking at the graph, I had reached a conclusion that there is no perfect trend line that captures the data, but one observation that I made was that if the CME has a lighter mass, it took longer time to reach Earth than a CME with a larger mass. And I want you all to think about why this is, and we will come back to this in a minute. The results show that on average it takes about 4 days to reach Earth and 45 minutes to cross Earth. That is the CME's path. If you want, you can pause the video to look further into the details of the projectile's trajectory. The conclusion that I had created for this experiment was that CMEs didn't have a clear relationship between mass and the time it took to reach Earth. The CMEs with the bigger mass took less time to reach Earth because when they are initially ejected, they are ejected with such a bigger force than CMEs with so smaller mass. Since there is no friction acting on a CME in space, then the CME will continue to move at the same velocity after initial acceleration. This is according to Newton's first law of motion, which is an object at rest stays at rest and an object in motion stays in motion in the same velocity unless acted upon by external forces. I believe my project is important. Through my research and my Java program, I had found that the average CME would take 4 days to reach Earth, and it would cross Earth for 3/4 of an hour. That is 45 minutes of no communication, no service, no GPSs, etc. Our technology-filled Earth would have no way of communicating with each other for this amount of time. What would be worse if the satellites that provided the network of communication would get destroyed in a geomagnetic storm caused by CMEs. If we didn't know about a CME headed towards Earth, then our satellites might get destroyed and we might not have any communication for a long time. This idea was brought to my attention on August 15, 2014. A CME had barely touched the Earth, but it destroyed many power lines in Russia. It is important to know how much time we have to protect our satellites and power grids before a CME comes closer to Earth. Using my Java program and SOHO LASCO instruments, we will be able to figure out how much time we do have so that we can prevent the tremendous damages coronal mass ejections can create. These are the sources for the video. I have hoped you enjoyed this demonstration about CME's trajectories.